Hello, welcome to another video. I'm going to keep it pretty simple for you guys. I'm just going to walk through a bunch of different AP problems, and whatever problems we don't get to, that's going to be y'all's homework, so it should be pretty straightforward. And that way you guys can see what kind of questions do they ask about derivatives specifically, how creative do these problems get, because they do get a little creative. You have to know what a derivative really is. You can't just get by with sort of memorizing formulas and that sort of thing. So let's go ahead and start on it. So number 2, wish I could zoom in a little bit more. Right, so I'm working through this guy. We have the graph of f, which is this like sort of jagged linear piecewise function. So with different slopes at different places. The question is, find f prime of 3. So what you have to realize is, well, what is this? What does f prime of 3 tell us? It tells us the slope of the tangent line specifically at x equals 3. But this is the tangent line to f of x, right? Not to f prime of x, right? The derivative. And we have the graph of f, right? So you just got to be very careful here. Sometimes they'll give you the derivative of f prime and ask a very similar question, right? So we have the graph of f. What would be the slope of the tangent line at 3 to this graph? Well, we would just sort of approximate it, right? So the point at 3 is here, and the tangent line would just be a line with the same exact slope as that segment. So all we need to do for this one is just calculate slope, right? What is the slope of this line segment? And it looks like that's 10 over 5, which is 2. All right. Okay, number 3. What is the instantaneous rate of change? Right, what is that? Instantaneous rate of change, if you don't know, is really just a fancy word for slope. We use this word when we're talking about typically word problems or real-world situations. So we'll see that later. But it's just the same kind of thing as slope. The slope of the function at x equals 2, or you could say, the derivative, right? We could say f prime of 2, like that. So with this function, 3x squared plus 5, let me write down the work over here. And we're doing this at x equals 2. Right, we want to find f prime of 2. So first off, what is f prime of x? Well, take the derivative. Looks like we get 6x. So f prime of 2, the instantaneous rate of change at 2, would be 6 times 2, which is 12. Now we don't have any units here, right? We would just say 12 is our answer, C. Okay, here's where things get a little interesting. Number 4. The function f is defined on the closed interval from -2 to 16. By the way, guys, if I'm going too fast, feel free to rewind, slow down. I just don't want this video to be an hour long. So that's why I'm going a bit faster. Okay, anyway, we're on the closed interval. The graph of the derivative of f is given below, right? So this right here is not f of x, right? This is f prime of x graphed as a function. So that's going to be a huge deal here. It says the point 6 comma -2 is on the graph of f of x, right? So like if you go here, that point is not on this graph, and that is totally okay, right? 6 comma -2, oh sorry, it actually shouldn't be here. It should be down here somewhere, right? That's totally okay. The derivative and the function don't have to overlap in any way. They don't have to have the same points, right? This is a point on the graph of f of x. An equation of the tangent line to the graph of f at 6, -2, right? This is our point. How do we write the equation of a tangent line? Well, if you have a point, the only other thing you need is the slope. So we want to know, for this new problem, what is the slope? The slope, right, at x equals 6 for this function. Now, how do we find that if we don't even have the equation for f of x, right? They didn't give that to us. All they gave us was this graph here. So let's think about it. The derivative, all we have are like points on this graph with inputs and outputs. What do these outputs represent? The y values. They represent the slope of the tangent line on the original f of x graph. Right, so if we want to find the slope of the tangent line at 6, right, this would basically be f prime of 6. What does this graph tell me this equals? 3 from this point right here, right? That point is giving you information about the slope of the tangent line on the f of x graph. Namely, if I plug in 6 into the derivative, I get an answer of 3. So this right here is my slope. That is my slope. So what do? Well, I take my point, I take my slope, I plug it into point slope form. 3x minus 6. So this gives me y plus 2 equals 3x minus 6. And there we go. Answer choice D. In fact, you could rule out any equation that has any other slope, right? Those other options do not have a slope of 3. All right, let's skip number 5. Let's go to number 6. Let me make some more partitions here. So this is for number 6. If f is a function for which the limit as x approaches negative 3 of, this expression here equals 0, then which of the following statements must be true? And in mathematics, when we say something must be true, that means it should be true in every conceivable possible way, no matter what f of x is, as long as this limit is equal to 0. Right? So just because you can find a couple of examples where, something is sometimes true, that's not going to be the right answer for this question. So let's look at answer choice A. The answer choice A says x equals negative 3 is a vertical asymptote of the graph. And, that's kind of something that you might think about because you look down here, right? When does this equal 0? It equals 0 when you plug in, right, negative 3. That's what makes it 0. But there's a huge issue with this answer in that we said, or we defined on our pink sheets, that you have a vertical asymptote when what? When this limit does not equal 0, when it equals plus or minus infinity, because that's what vertical asymptotes do. Your y values explode in value, right? They shouldn't approach any real number. You should have unbounded behavior. So by definition, there's no way this limit is telling us there's a vertical asymptote. So that's wrong. Answer choice B, the derivative of f at x equals negative 3 exists. Is that true? Do we know that for sure? Should that always be true? Well, this limit for sure is, what we call the alternative definition of the derivative, right? We wrote that on the pink sheet, and it's applied at a value of, negative 3. So this seems like a pretty good option. Let's look at the others, just be safe though. Does f have to be continuous at x equals 3? Not necessarily, right? So we know this. You could have a little hole at the place where you're approaching, and that's perfectly fine. The limit would still be equal to, whatever number is at where the hole is, right? If that hole had a y value of 0, the limit would be unchanged, even though we are obviously not continuous there. And again, for the same reason, D is wrong too, right? I don't have to have an output right here for the limit to exist. And clearly the limit exists. We have an answer there. It equals 0. So it looks like B has got to be our correct answer. So the derivative of f at x equals -3 exists. Cool. All right, let's keep going. Okay, a few on this page. The graph of the function f given below consists of 3 line segments. Find this limit and check that out. What is that? That's the definition of the derivative, but applied specifically, typically we see an x here and an x here, right? But in this case, we're applying that definition specifically at an x value of 3. So what is this, right? This isn't the derivative as a formula. This is the derivative, f prime, but evaluated at 3, right? It's the derivative of f evaluated at 3. So this is some kind of numerical answer, right? We should get some sort of number here. Okay, if you are able to piece that together, now you have another trip here, because this graph is the graph of just f, not f prime. So how do we get the answer to f prime of 3 by looking at the graph of f? We get the answer by looking at the slope of the tangent line, specifically at 3, right? So at this point, what is that slope? It's a line like this, right? A line pretty much right on top of that one. So this answer must be the slope between the 2 points that make this line segment, right? Namely 0, 4 and 6, 0. So if you use the slope formula, 0 minus 4, 6 minus 0, you get an answer of -2/3. Answer choice B. Notice they're going to hope that you do the slope formula upside down and fall for this answer here. They always love to lay traps for you guys. Okay, cool. Number 3, we have a piecewise function. It's kind of weird, right? So we have a rational function. As long as x is not equal to 5, our function looks like this. If x equals 5, then our output of the function is 5. Okay, kind of a weird function. But let's just see what the question is. Which of the following statements about f are true? The limit, let's look at number 1. The limit as x approaches 5 of f exists. Okay. If x is approaching 5, what does that mean on the graph, right? It does not mean that we go to the output specifically at 5. What we look for is, okay, what's happening around 5, which is the concern of this piece of the function here, right? X is not equal to 5, but if it's a little bit less or a little bit bigger than 5, this piece of the function is engaged. So the point is, if I can take the limit of that piece and it gives me a numerical answer, then that limit exists, right? So the limit as x approaches 5 of x squared minus 5 over x minus 5. Well, this looks like a typical sort of whole example, right? We would have x minus 5 times x plus 5 over x minus 5. And there is our whole right there, right? We get rid of the whole, we plug in the 5, and we get an answer of 10, right? So yes, the limit as x approaches 5 of f exists. Cool. Is f continuous at 5? So what do we mean by continuity? What does it mean to be continuous? The definition of continuity would tell us that the limit as x approaches 5 of f first needs to exist, which we've showed that it does, but it also needs to be equal to f at 5, right? The actual output at 5. Well, we know what this limit is. We found that earlier. That's 10. What is f of 5? Well, for this, you got to go all the way back to the definition of the function. If x equals 5, the output is 5. And so the right side of the equation turns into 5. And these are not equal, right? So because of that, we are not continuous at 5. For continuity, we need this to be true, and it is clearly not true. Okay, so 2 is wrong. We can already scratch off whatever answer choices have 2. So it's either 1 only or 1 in 3. So is f differentiable at x equals 5? We haven't totally talked about differentiability yet. Basically, what that means is, does the derivative, what this means is, does the derivative exist at x equals 5? And this is more of a conceptual thing. This is not really something that you can just memorize a formula for. So let me draw a picture of our scenario here. All right, so if you think about what this function looks like, it becomes really clear. So like this piece over here, there's a hole at 5, but otherwise, other than the hole, the function looks like x plus 5. Because no matter what x's I plug in here, whatever this number is will always cancel with this number. So effectively, this is my function, basically, as long as I don't plug in 5. That's what that means. And x plus 5 is a really easy function to graph, right? So let me do some graphing here. I'm going to go by 2's maybe on this axis. 5, 6, 7, 8. It's going to be 2, 4, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Once I get to a value of 5 for this function, I should approach a value of 10. Right? So essentially my graph looks like this with a hole here. But then at 5, my output is 5. So I have a little point here. Okay, here's where the conceptual idea of the derivative, like how we came up with this, right? Remember, think back to our pictures of what we did to create the slope of the tangent line. We would always pick a point, sort of some distance away from the point at 5, and then we would calculate the slope of the secant line that connects those two, right? And then we would move the point a little bit closer and calculate that slope. And then we would move the point a little closer, calculate that slope. And the limit of these slopes, the slopes of these secant lines, is what we call the derivative. Now, what are these slopes getting or approaching, right? So on the left side, these slopes are approaching, I guess we could say m is approaching a slope of negative infinity, right? If I were to choose a point really, really close to this hole, the secant line is almost vertical. Okay, now let's look at the right side. It has to be true for the left and the right. They both have to approach the same thing. If I take a point over here and I connect it with this one, and I take a point a little closer, connect it, point a little closer, connect it, point a little closer, connect it. What are these slopes approaching? M is approaching positive infinity, right? For a derivative to exist, the slopes of these secant lines on either side have to both approach the same number, right? It has to be a number and it has to be the same number. Now in this case, we're approaching infinity. That's the first red flag. But the second red flag is they're not even the same infinity, right? So 3 is false. This is the kind of thinking you have to do to go through this problem. It's not really another way to do it. So in this case, it was only 1. That's a pretty tricky problem. It's a little higher difficulty there. Okay. let's try some real world stuff now. So oil is leaking from a tank. The amount of oil in gallons in the tank is given by this function. So you plug in a time, it spits out the number of gallons in the tank. Keep it simple. From 0 to 24, T represents the number of hours past midnight. Okay, so that might be important later. First of all, find G prime of 5, specifically using the definition of the derivative, right? So if you try to use some kind of rule, you're not getting the points for this. This would be an FRQ question. If they do not see you use the definition of the derivative, you get no points, right? So what is that in this situation? That would be the limit as h approaches 0, g of 5 plus h minus g of 5, all divided by h. Now, they may also give you points if you use the alternative form, right? So we could also say the limit as x approaches 5 of g of x minus g of 5 divided by x minus 5. Both these limits should agree with each other. They should both give the exact same answer. So I believe on the AP test, they would give you points for creating either of those, right? One of them might be easier to use than the other. And I don't know which one would be easier, but we could try maybe the one with h's, maybe we could just try that. Or you know what, actually, maybe the top one would be easier. I can see there's a t squared in there. If I plug in 5 plus h, I'm going to have to expand a binomial, right? So I can avoid that if I use the top version, right? So let's see. See what this does. X approaching 5. G of x is 4,000 minus 3t squared. And then I have minus, make sure to put big parentheses here, for g of 5. So when I plug in 5, I should probably calculate this value. So this is going to be 4,000 minus 3, looks like times 5 squared, which is 25. Okay, so that's 4,000 minus 75, which is 3,925. Okay, so minus 3,925. All divided by x minus 5. Oh, and you know what? G of x, this t should actually be an x here. So it should be 3x squared, right? Because I'm plugging in x. Okay, so we're gonna couch that limit and just keep going with this first one. So the limit as x approaches 5. 4,000 minus 3,925, that's 75. So we end up with 75 minus 3x squared over x minus 5. Okay, now clearly if I plug in 5 into this limit, you get 0 over 0. So that tells me there's a hole somewhere, right? So I've got to factor some things probably to find out where this hole is. And I would start by factoring out a 3 out of the top. In fact, I would factor out a negative 3 so that I get this x squared first, and then I get minus 25. I want the x to be positive because in the bottom, my x is also positive. And it looks like we have a nice little difference of 2 squares. So let's keep going. Let's keep factoring. Don't forget about that negative 3. I bet you they're hoping you forget about it. All right, so we factored the difference of 2 squares there. It's all over x minus 5. This cancels with this in the limit, right? We're left with, let's plug in the 5 now. We get 5 plus 5 in the parentheses. It's negative 3 times 10. That's negative 30. Cool. So this is g prime of 5. So because this is a real world problem, we have to have units. I guarantee you they have a point allocated for units here. So what are the units? Remember, the derivative is a rate of change, right? So if we're talking about gallons and we're talking about hours, the derivative, the rate of change of this thing would be gallons per hour. Okay, cool. So this answer to part A. And then part B says using appropriate units. Oh, looks like we already guessed they were going to ask us that. Interpret the meaning of g prime of 5 in the context of this problem. So not only do we have to calculate this number, we have to actually explain this. What does this actually tell us? So part B, this is part A. So in part B, we could say that the negative 30, or let's say this. Let's say g prime of 5 represents the rate of change in gallons per hour of the amount of, is this gas? Oil. Amount of oil in the tank at, they said T represents the number of hours past midnight. I told you guys not to forget that. So if in this case we're dealing with 5, then this would be at 5 a.m., right? At 5 a.m. And yes, the AP grader would expect to see some kind of mention of time at the end. They want to hear you guys use this rate of change, gallons per hour language, and it's of the amount of oil. They'd be looking for those 3 components, to give credit for this problem. So yeah, that's kind of tricky, right? You can't just memorize a formula and move on. You got to know what you're doing. Now, I bet you some of y'all might want to try out using this for the same problem. You should get the exact same answer of negative 30. Right, so maybe try that out and see if you get it. It should be the exact same number. But I don't have time for that. I got to move on. So number 11, a rod of length 12 centimeters is heated at one end. The table below gives the temperature T of x in degrees Celsius at specific numbers, x centimeters, from the heated end. So our units here are Celsius, degrees Celsius, and centimeters, not time here. So that's kind of interesting. You typically don't see that. So part A, this is typically the easier part. Use the table to approximate T prime of 8. So remember, what is this? This is the slope of the tangent line at x equals 8 to the function T of x. Right, and we have the table for T of x, which is great. The problem is we don't have an equation, but that's okay, right? If you don't have an equation and you can't find the derivative, what you do is you do the next best thing, which is take 2 points that are very close together around 8, and then just calculate the slope between them. So namely, right, you probably want to use these two. Right? They might actually give you credit if you use the one at 5 and the one at 12 because they sort of evenly, they're kind of evenly distributed on the left and right of 8 as well. But you want to use the closer points if you can, right? So we would want to calculate the results. Oh shoot, let's see. Yeah, so we want to calculate the slope here. So remember, these are your y values, these are your x values, right? These would go on top. 54 minus 60 over 9 minus 7. So that would be negative 6 over 2, negative 3. What are the units? The units here would be degrees Celsius per centimeter, right? So what that's saying is for every extra centimeter, if you started at 8 and you moved an extra centimeter to the right, you would roughly lose about 3 degrees Celsius. or that you would measure a temperature 3 degrees Celsius less than the temperature at 8, right? So this is what that represents. So this is part A. Part B, again, using appropriate units, we already have those, right? Interpret T prime of 8 in the context of the problem. So T prime of 8 represents, right, the rate of change of the temperature in the rod, or sorry, I guess we could say of the rod at x equals 8 centimeters in degrees Celsius per centimeter, right? They're looking for, you notice how I'm kind of using the same language between these two part B's, right? You want to mention something about a rate of change. You want to include your units. You want to mention specifically where, right? Because this is specifically T prime of 8. T prime of 8 could be different from T prime of 0, T prime of 1, T prime of 10. This is at a very specific spot in this rod, right? So you want to mention that. So very important to get the full credit for those. Okay. Let's see, how many more? Okay, so we have 1, 2, 3, 4, 5 more to go. And then the rest, I think, I'll give you guys for homework. So number 1 is a layup here, but they're hoping you make a very simple mistake. What is g prime of x if g of x is just x? G prime of x, if you just take a derivative, is equal to 1. So if I plug in 7, what do I get? Well, there's no x's over here, right? So it doesn't matter what I plug in. I still get an answer of 1. I guarantee you, though, many people are choosing 7 because they think, oh, well, if I plug in 7 here, then I get 7. No, that's g of x. We're asking about g prime of x, right? Different function, the derivative. Okay. Number 2, this one might take a little bit more work. So the line x plus y equals k, they don't give us this number, it's a constant, is a tangent line to the graph of the function, this guy, x squared minus 5x plus 2. What is the value of k? Okay, so here we have the tangent line, but we're missing some information about it. And I have the function, and I need to somehow solve for this k value. That's kind of weird. Okay, well, let's start with what we know. So if we have the equation of the function, chances are it's going to be a good idea for us to take the derivative. So let's go over here and find f prime of x, right? That's going to be, looks like 2x minus 5. Okay, cool. Okay, and that's a tangent line to this graph. In fact, you know what? If it's a tangent line, then the slope of this line should at some place equal this derivative, right? This should equal the slope at some point, right? So how do I find the slope of that line? Well, let's just rearrange it, right? The tangent line here. If I just solve for y, I get y equals negative x plus k. Okay, so now we can kind of see what this is doing here. So if you look at the original function is a parabola, right? I don't know exactly what it looks like, but it's a parabola. This k value is controlling, this k value is essentially the y-intercept for the line. And you can imagine, right, if I started my line here and I just sort of move it up, right, by increasing the k value, eventually it will touch the graph at exactly 1 point. But if I keep increasing the k value, it will no longer be a tangent line. So there's only one k value that makes it tangent, right? So what do I need to do here? I can see that my slope of the tangent line is -1, right? So the idea is my derivative for some x value is equal to -1. So that's kind of interesting. I don't know if this is going to help us here, but let's see. So if I solve this, right, I get 2x equals 4. I get x equals 2. Okay, so what is this telling me? This is telling me the x-coordinate of my point of tangency, right? I know the x-coordinate is 2. Interesting. How can I find the y-coordinate? I can find the y-coordinate by finding f of 2, right? Plugging into my original function over here. Over here, right? X squared minus 5x plus 2. So that's going to be 2 squared minus 5 times 2, and then plus 2. Don't forget the plus 2. I'm just trying to find out as much information as I can. I'm keeping my work very organized, right? That's always a good rule of thumb. So yeah, my y-coordinate for this point is -4. Okay. Is that going to help us? Yeah, I think it will, right? Because this point right here, not only is it on the parabola, but it's on my line. Which means I should be able to plug in 2, -4 in for x and y. And let's see what this does for us. -4 for y. I get -1 times 2 plus k. Now I have an equation with only k in it, and I can solve it, right? So keep going. -4 equals -2 plus k. That means that k equals -2. Cool beans, right? And is that an answer? Let's just check. Yes, it is, -2. Now, there might be another way to do this. If you think back to when I had you guys find a tangent line to a quadratic, you could do this fully algebraically using that really crazy complicated method I showed you that one day in class. And once we learned the definition of the derivative, we basically threw it away. But that would actually work here too. You just have to be very creative with it. This is probably the way they actually want you to do the problem though. Just using derivatives, using tangent lines and how they connect with each other. They want to see you connect those ideas. Okay, so that was number 2. Number 2. We did number 1 real quick on the page. All right, let's look at number 1 over here. What is the instantaneous rate of change at x equals 2? Remember, that is another way of saying the derivative at x equals -2, or another way to put it, f prime of -2, right? We have the f function, so we can actually just apply. In this case, it looks like we're going to have to do a combination of the quotient rule and the chain rule here, right? So let me rewrite the function. And I'm actually going to do this in slow motion a bit because you're having to use 2 rules at once. So you just have to be careful. So f prime of x. So the first thing that we sort of tackle is the fact that this is a quotient, right? So this is like, you have a function divided by another function, right? This is, typically what we call f, although that's kind of confusing because we have f here, but I'll just keep it. And we typically call this g. Remember, the quotient rule would be the derivative of the top, or the first, times the second, minus the derivative of the second times the first, divided by the second squared. All right, so I'm just going to plug those things in. Derivative of the first, the top function, that's 1, times the second, just keep it the same, minus the derivative of the second. Oh, okay, we don't need the chain rule here. We can do that, right? That's just going to be 2x times the first, x minus 1. divided by x squared plus 2 squared. Don't forget the squared. And remember, the goal here is we're trying to evaluate this at -2, right? So don't expand the bottom, but try to simplify the top as much as you can, right? So I'm going to distribute that -2x into both of those, and we just want to clean up this numerator, right? So this will stay the same. -2x times x, that's -2x squared. -2x times -1 would be plus 2x, and this is all over x squared plus 2 all squared. Cool. And then this is going to be, we have some like terms, so we get -x squared plus 2x plus 2 all over x squared plus 2 squared. Woo! All right, so that is my derivative. Now let's plug in -2. And again, be just really careful here, right? When you plug in -2, make sure you put parentheses for every single x. In fact, that's what I'm going to do first. I'm not even going to put in the number first. I'm going to just set up my parentheses. I guarantee you this is where you guys are going to make your mistakes. If you try to do it all at once, you're going to make mistakes. So set up all the parentheses first, so you're absolutely clear. Now I'm going to put in the -2, right? So -2. Notice how I have 2 minus signs there, right? -2, -2. Now we're going to calculate. -2 squared, that's going to be +4, but I got that other minus sign. So I get -4, and then I get another -4, and then the plus 2 there. Down here, I get 4 plus 2 is 6, all squared. So let's keep going. -8 plus 2 is -6 divided by 36. So this is -1/6. -1/6. Is that an answer? Yes, it is. Answer choice A. Awesome. Okay, number 3. F, G, and H are non-zero differentiable functions of x. So all that's saying is we can take a derivative of any of these 3 functions and they exist. So here, there's no numbers, no equations. You just have to know how to apply the product and the quotient rule in this case. Because notice there's a product up here, but we have this divided by some other function. That's a quotient as well. And which rule do you do first? In this case, right, think about what is inside of what, right? The product is inside of the quotient, right? And just like with onions, just like with chain rules, right? Just like with ogres, you have layers here. You always start with the outer layer. You apply whatever rule applies there, and then you apply the stuff for the inner layers if necessary. So we have to start with the quotient rule. So derivative of the first. So that's going to be, I'm going to write it as this whole thing with a little prime. I'm going to take that derivative later, right? I'm just going to set it up here. Times the second minus the derivative of the second, f prime, times the first, divided by the second squared. So that would be f squared. And already we can cross off answer choice C, which is awesome, right? And we might be able to cross off some other things too. So, I mean, you notice there's clearly a minus sign there, and there's no minus signs here. So that's got to be wrong as well. It's either between A and B. You can only figure that out if you keep going with the problem. So, oh, whoops. So now what I'm going to do is I'm going to expand this. I'm taking the derivative of this product now. I've got to expand that out. So what does that look like? Well, let's put a bigger set of parentheses and write the rest of my derivative just as it was. And I'm only going to expand out that one first parentheses for, I'm taking the derivative of g times h. The product rule says derivative of the first times the second plus The derivative of the second times the first. Cool. So if I distribute this f in here, which I can do, it's a distribution situation. You want to list these in alphabetical order, right? Notice how, right? It's always FGH or GH, right? So, you know, the first term is F times G prime times H plus, this will be F times G times H prime minus F prime times G times H all over F squared. Did I not put squared here? Oh, that's interesting. F squared on the bottom. Which one is that? That is answer choice A. Answer choice A. Yeah. So there we go. That was a long problem. That was number 3. Okay, and now let's just end it with number 5. Number 5. I'm going to do this one in a different color. I think we're coming up at the end here. All right, so number 5. We're taking the derivative of that mess of stuff there, right? So keep in mind, right, the derivative, you can do it to each piece as long as they're not being multiplied together, right? If they're being added or subtracted, you do the derivative of each one separately, right? So we could, you know, we could do the derivative of this one minus the derivative of this one. Notice how I pulled the minus to the outside. That's fine. You can actually do that. And this plus sign stays out there too. Derivative of 1 over t. So let's just find this derivative first. What I would recommend, you know, the first one's pretty easy. You get 2t. I would recommend rewriting this guy, right? What's another way to write it so that we could use the power rule? This is t to the negative 2. Right? This one over here is t to the negative 1. Now I can see what the power rule is going to tell me the derivative looks like. All right, so I have minus, parentheses, plus, parentheses. Now I'm going to do these derivatives. Right? I get negative 2 times t to the negative 3. And then over here, negative 1 times t to the negative 2. Remember, you're subtracting 1 from each power. And with negative powers, that means the number kind of gets bigger. It just, you know, it's negative 3 it has a bigger size than negative 2. So, you know, just keep a lookout for that. Here I have 2 minus signs. That's a plus. So 2t plus. This is going to be 2 over t cubed. And then over here, I get a minus, so minus 1 over t squared. All right, do I have that as an answer? Oh, no. So now we have to evaluate it at 2. Cool. So now I plug in 2. I get 2 times 2 plus 2 divided by 2 cubed minus 1 over 2 squared. So 4 plus, this is going to be 1/4 minus 1/4. All right, so these cancel. We get 4. What do you know? Sure enough, that is an answer. So all you guys have to do, I'm giving you guys some AP problems. I'm going to see if y'all can do them. So I'm going to zoom in on each of them individually. I would just pause the video, take a screenshot, and then post the pictures into like a Notability sort of page, an empty page. That way you can kind of work them out there, and it will be really easy to upload them from Notability as PDFs into my SJ, right? Just, you know, this little share button at the top right, Notability has a similar thing. And you can typically, if you click like send copy of a page, it will make it a PDF automatically. See, it's already doing that for me. I'll upload these notes later. Let me go ahead and first zoom in on some of these problems for a second so you can take some pictures. All right, so here is, you know, I want y'all to do 1, 2, 3, 5, 6, and 7. Okay. And then down here, I'll zoom out a little bit. I want y'all to do 1, 3, and 11 from this page. I mean, you notice there's some E stuff going on here. We haven't gotten to E, haven't proved the derivative of that yet. It's kind of a whole can of worms I don't want to get into. All right, so this is y'all's homework. Yes, I'll actually be grading it. And take care, enjoy your asynchronous day, and good luck.